Okay, now let's talk about circular motion. In previous chapter, especially like kinematics of linear motion, okay, you learn about these. Let's say if the acceleration and velocity has the same direction. For example, like this person pushing on the crate, so the force is to the right. So when the force is to the right, okay, I want to write something. Okay, like force is to the right, so force is equal to ma. Okay, so the acceleration direction will be the same direction with the force. So what I can say is the acceleration on the object is also to the right. Yeah, the acceleration on the object is also to the right. So if the acceleration and velocity, yeah, in the same direction, yeah, or we can say when the force is parallel to the velocity, so the acceleration also parallel to the velocity, what happened to the object? The object will move faster and faster forward. Okay, the object will move faster and faster forward. Velocity increases. Okay, so velocity will increase when velocity and acceleration in the same direction. Yeah, or we can say when the force and the velocity is in the same direction. However, later you learn about projectile motion. Okay, this time you learn about this acceleration due to gravity. Yeah, especially like the weight of the car, which is the gravitational force. Okay, this gravitational force is equal to we can say mg. Okay, mg. Actually, the acceleration due to gravity is actually the acceleration due to gravity is ag. Yeah, is directed downward because we can say this acceleration due to gravity is the gravity itself, isn't it? Okay, maybe I should write something here, negative g. Okay, because the weight is downward, so the acceleration due to gravity also downward. So what happens if, like, you see, when the force is perpendicular to the velocity, or we can say when the acceleration due to gravity is perpendicular to the velocity, what will happen to the car? The direction of the velocity will change. I mean, the velocity will change direction. It will not move straight forward. Okay, it will change direction. Yeah, it becomes like a parabolic path. Yeah, the path become a curve, isn't it? That is when the force is at an angle with the velocity or perpendicular to the velocity. So it will change direction. Okay, but if the force is or we can say the acceleration due to gravity is parallel to the velocity, yeah, the velocity will increase in the magnitude. Yeah, will change the magnitude. Will change in the magnitude, but will change in the magnitude. Yeah, the velocity will change magnitude, but if the force is perpendicular to the velocity, becomes like a projectile motion. Okay, it will change direction. So this is this is why that is the reason why we have circular motion now. Yeah, so let's look at the forward slides. Now we are going to learn about uniform circular motion. Okay, what is meant by uniform circular motion? Uniform itself means the circular motion, like you see this stone, it moves in a circular motion. Okay, firstly, the uniform, it means constant speed. It moves. You can imagine this stone. It's swirl in a circle with constant speed. It never get faster or slower. Yeah, constant speed. Constant magnitude. Yeah, or we can say constant in the magnitude. Okay, constant speed. That is called uniform. Now, circular motion. What does it mean by circular motion? That means the direction of the velocity. Yeah, when talking about the velocity, you have to move in a circle. in order to move in a circle, the velocity has to change direction, isn't it? Circular motion. Circular motion, that means the velocity of the object have to always continuously change direction in order to move in a circle. Okay, so the velocity have to change direction to move in a circle, but in terms of magnitude of the velocity is always constant. The speed of the object is always constant. The magnitude of the object is always constant. But in order to move in a circle, the velocity have to always change direction. Okay, have to always change direction. Like you see at the top here, the velocity is to the left. But move to this position, the velocity become downward. At the bottom, velocity is to the right. And over here, velocity is upwards. So velocity always change direction. If you see over here, velocity is this direction. Over here, velocity is this direction. You see, always change direction. You see that? It's always change direction. That's why when talking about velocity, it's also changing. For speed, it is constant. Speed is what we call a scalar quantity. But velocity is a vector quantity. Why scalar quantity is constant? Because the magnitude is constant. But when talking about velocity, velocity is a vector. It is vector consists of both. It consists of what? It consists of both magnitude and direction. In terms of magnitude, the uniform circular motion always constant. But when talking about direction, the direction continuously changing. Because there is a one component in the vector changing, for velocity in the circular motion. So one component of the vector, which is the direction, is always changing, although the magnitude is constant. So this vector also change. So the velocity also change. The velocity also changing. Velocity considered changing because of changing direction. Other vectors, like sometimes the question will say, what kind of other vectors change? Momentum. Momentum also change. Okay. What other vectors? Which consists of velocity. Right now is the momentum. All right. But maybe you can talk about the kinetic energy. If kinetic energy is a scalar quantity, so that one is considered constant. Constant kinetic energy, because talking about the speed, the magnitude is always constant. So for kinetic energy is also a scalar quantity, is considered constant. However, for vector quantity like velocity and momentum, they are vector quantity. They have direction, so they're considered changing. Okay. All right. So because of velocity changing, because of changing velocity, that's why because of changing velocity, that's why they have what we call acceleration. Because we have changing velocity, so we have a delta v, isn't it? We have the delta v. We have changing velocity. Okay. When velocity change, that means they have acceleration. But this type of changing direction velocity is caused by centripetal acceleration. We have a special name for this acceleration. We call it centripetal acceleration. So here it shows the direction of the centripetal acceleration. Okay. So let's look at this one. In this case, we have centripetal force. because we know when you have acceleration, that means you have resultant force. You have resultant force. You must have a force that caused this acceleration based on Newton second law. Total F equal to ma. Total F equal to ma. But this resultant force here is the centripetal force. So this acceleration for this centripetal force is also called centripetal acceleration. Okay. Now, I want you to look at this one, this diagram. Okay. So just like the example just now, talking about the projectile motion, why the velocity change direction? Why the velocity change direction? Because there is a force perpendicular to the velocity, isn't it? Like this car, there is a gravitational force pull downward while the velocity is moving to the right. So this car cannot move straight forward. It will change direction downward. Yeah, it will change direction. So similarly to this one, like this stone, if I swirl in a circular motion, because there is a string, there is a rope tied to the stone. This rope cannot escape the string unless the rope break off. Then only the stone will move forward in a straight line. But because there is a rope tied to the stone, this stone cannot escape the rope. Yeah, it is you're holding on the stone. You see that? You're holding on the stone, yeah, through a rope. So actually, when you try to throw the stone, actually it moves in a circular motion because you are holding on the stone through a rope. So there is a tension force. Tension in the rope, yeah, tension in the rope pulling on the stone to the center of the circle. To the center of the circle. Yeah, continuously. When the stone moves to this position, the tension is to the right. Yeah, because you are still holding on the stone. Yeah. So you yourself, when you're holding on the stone, holding on the rope, you'll feel tension in the string. Yeah. In the other way around, you also feel there is a tension pulling on you, isn't it? This is what we call action-reaction force. Okay, the rope actually pulling on your hand. That's why your hand feel the tension. Yeah, while you try to swirl the stone in the circular motion, you feel that you feel the tension in the rope. You feel the tension in the rope. While at the same time, the stone also feel the tension to the center of the circle. I feel the tension to the center of the circle. That's why the stone cannot escape from your pull. Cannot escape from your pull. It will just maintain in the circle. It just maintain in the circle. How long is the rope? That means how long is the rope? That is how far the stone can be. That means this rope will become straightened. So as long as this stone will maintain at the same distance from the grip, based on the length of the rope. You see that? So you yourself, you feel the tension in the rope towards the stone. When you try to make it move in a circular motion, you feel the tension in the rope. The stone at the same time feel the tension or the pulling force toward the center of the circle. Okay. Now I just want to rub this off. Okay, I will rub this off. I just want you to focus on these several things. I just want you to focus on these several things. So just now when talking about the tension, this tension is the one who responsible for the stone to move in a circular motion. Just like what you learned before in a projectile motion, the gravitational force is the one who responsible for the velocity to change direction into a projectile motion. Yeah, the gravitational force is the one who responsible for the velocity to change direction, become a projectile motion. So in this case, it is the tension, because this tension also 90 degree. You see that? This tension also 90 degree to the velocity. And this tension is the force that responsible for the velocity to change direction, velocity for the stone to change direction into a similar circular motion, just like the projectile motion just now. You see that? Just like, because this one, the force, maybe let me draw it out. The velocity of the car is to the right, but the force is perpendicular to the velocity. That's why it become a projectile motion. Okay, become a projectile motion. This time it is what? It is the tension that is perpendicular to the velocity. Yeah, last time is the gravitational force. This time is the tension in the string. It is the tension that is 90 degrees to the velocity. That's why this stone becomes like moving in a projectile motion. Not really projectile, but it's a circular motion. You see that? Keep on continuously change direction. The tension is always 90 degrees. When the stone is over here, the tension also 90 degrees to the velocity. At the bottom here, also 90 degrees. Over here, tension always 90 degrees, always perpendicular to the velocity. So that's why the velocity keep on changing direction. So this tension force become the centripetal force. This tension force become the centripetal force. So centripetal force actually is a resultant force from the existing force. You see, in this diagram, I don't draw centripetal force. I draw the tension. You actually cannot draw centripetal force on the stone because this centripetal force is from existing force. What are the forces exist on the stone right now? What are the forces exist on the stone right now? You have the tension force. Okay, when you draw the free body diagram, this stone is connected to a rope, so there must be tension on the rope. Another thing, of course, this example, I neglect the weight of the stone. Yeah, I neglect the weight. Yeah, since this one is like a vertical circular motion, then actually must also have the weight of the stone. Yeah, let me draw it out. Actually, got one more force. It's called the weight, mg. But for this all of this example, there is the weight also mg. But I try to simplify the diagram. Okay, there is actually mg. So this mg also responsible for the velocity to change direction. The tension plus the mg responsible for the stone to change direction. But if you look at other position, this mg become parallel to the velocity already. Actually will make the stone to move faster and faster. But actually that's why I neglect the mg. I don't want to complicate things. Okay. So what I can say is centripetal force is actually come from the existing force, like from the force, tension, and mg. The tension and mg. So these two forces, tension plus mg, they are the centripetal force. So centripetal force is not another force. They are actually the existing force. They're actually the resultant. What I can say is the resultant of the existing force. So what I can say is, for example, like the top position, the resultant force in the y component, it is the tension. The resultant force is actually in the y component is the tension. I'm talking, let's say the top position. Okay, it's the tension plus mg actually. Yeah, maybe I should rewrite this thing. Yeah, because I neglect the weight. Yeah, just to simplify things. Actually, let's say like the top position. At the top position, yeah, there are more example in the problem videos. You can look at the problem videos to we will draw more detailed free body diagram over there. Yeah, like the top position here. What's the resultant force experienced by the stone? The resultant force experienced by the stone happens at the y component. The y component, they have the tension plus the weight. Tension plus the weight. Okay. And these forces become the centripetal force. These forces, tension and the weight, become the centripetal force. Centripetal force is the centripetal force is the symbol Fc. It is the resultant force. Resultant force from the existing force. This tension and the mg is the existing force. They are the existing force, the tension and the weight. Okay, they combine, they become the centripetal force. So we know that total F equal to ma, isn't it? This whole thing actually equal to ma, right? The resultant force equal to ma, and okay, and this acceleration over here become the centripetal acceleration, and this one is a centripetal force. Okay, so when you have centripetal force, okay, when you have centripetal force, you must have centripetal acceleration. You see that? When you have a centripetal force, you must have centripetal acceleration, because it's all because of what we call Newton's second law. Let me write it down over here. Yeah. Hold on a second. So these all are because of Newton's second law. Newton's second law. Okay. Clear? So it is a second law. Total F equal to ma. Alright. I hope you are clear. Yeah. It's because of Newton's second law. Total F equal to ma. So the total force over here is actually the centripetal force. And the acceleration caused by this centripetal force is called centripetal acceleration. Okay, it's the resultant force from existing force. So from the top over here, actually, actually it's not just the tension. It's the top over here, the centripetal force actually is talking about only the top position, because at the bottom, the resultant force become different. Yeah, the resultant force become different. So at the now I'm just talking about the top position here. Yeah, the top over here. The centripetal force is the tension plus the weight. The tension plus the weight. Okay. So it's the resultant force from the existing force. Okay. So when you draw the free body diagram, of the stone, don't draw centripetal force, because centripetal force is not separate force. It's not a separate force. It's a resultant force actually from the existing force. You just draw the how you draw the free body diagram on the top position. How you going to draw? The free body diagram for the top position? You just draw. How you going to draw? Okay, just a point mass to represent the stone. Okay, and then you draw the tension. Okay, you draw the tension, and you draw the weight, and then you draw what? You draw the centripetal acceleration. Centripetal acceleration downwards. That's all. Okay, that's all. Don't draw the centripetal force, because centripetal force is not a separate force from the tension and the mg. The tension and the mg, both of them they are what? They are the centripetal force. Both of them they are the centripetal force. Combined they are the centripetal force. So don't draw the centripetal force on the point. You just draw tension and the weight. Okay. So the tension and the weight, they are the centripetal force. Okay, I will explain more in the problem videos. Now, centripetal force and acceleration always perpendicular to velocity and directed towards the center of circle. So this centripetal force, the tension, like I say, this tension is always perpendicular to the velocity, perpendicular velocity, and always directed to the center of the circle. Because they are always perpendicular to velocity, that's why velocity always change direction. The velocity always change direction, because the force, the tension is always perpendicular, okay, and directed to the center of circle. Yeah, you see at the bottom here, the tension is towards the center, AC also towards the center, and over here AC also towards the center, tension also towards the center, always towards the center, always perpendicular to the velocity. Okay, now what are the examples of centripetal force? So here are other examples of centripetal force, like you can see. Just now, tension is one example. Tension is perpendicular to the velocity, so tension provides the centripetal force for the velocity to continuously change direction in a circular motion. Tension is one type of centripetal force. What other types of centripetal force? The frictional force. The frictional force, like we see the car, yeah, move in a circular motion. Okay, you see that in a round. Let's say this is a roundabout. Okay, you want to make a U-turn. Okay, not a U-turn actually. All right, you turn 270 degree. Okay, so this car, you want to make a turn. This car also experiences a circular motion, isn't it? You move in a circular motion. But how can the car move in a circular motion if there is no friction on the road? So that's why the car must be rough enough. Must be a rough road. This must be a, or you can say, it must be a rough road, especially a dry road. Dry road has a lot of friction. The frictional force is very important. Yeah, the frictional force is very important for the car to move, to turn, to make a U-turn. Yeah, the frictional force on the road. Yeah, this is by the road. The road must have enough friction. The road must have enough friction for the car to turn. If the road does not have enough friction, like during a rainy day, it's very very dangerous for the car to make a U-turn, because anytime the car will skid, yeah, will lose grip from the road, and accident will happen. Cannot make a successful U-turn. Yeah, or if the car move too fast, the road does not have enough friction. It's very dangerous for the car to move in a circular motion. Yeah, to make a U-turn on the road. So the car making a U-turn on the road is also a circular motion. The road must have enough friction to grip on the car in order for the car to make a turn on the road. Okay, frictional force is one type of centripetal force. It is one type of centripetal force. As you can see, the friction here also directed to the center of the circle, center of the U-turn. Yeah, center of the U-turn, and it is also perpendicular to the velocity. Perpendicular to the velocity. That's why the velocity can change direction. Because it's perpendicular 90 degree. That's why the velocity can change direction. Okay. Now, how about the satellite? Satellite also revolve around the Earth. So why the satellite can revolve around the Earth in a circular motion? Because there is a gravitational force pulling on the satellite. Yeah, we know that gravitational force always directed towards the center of the Earth. Center of the Earth. So the center of the Earth is also the center of the circle of the satellite. Okay, so this gravitational force experienced by the satellite also become the centripetal force necessary for the velocity to change direction in a circular motion. So this gravitational force become the centripetal force for the satellite to move in a circular motion around the Earth. Why this gravitational force can change the direction of the satellite into a circle? Because this gravitational force again is 90 degrees perpendicular to the velocity of the satellite. Okay? The tension is like what I mentioned just now. The tension becomes the centripetal force for the stone to move in a circular motion, to continuously change direction, to move in a circular motion. Like for the roller coaster, this is a roller coaster. How can the roller coaster move in the loop? A loop is also a circular motion. You see the track? You see the track is a loop. How can the roller coaster move in a loop without the track? First of all, you must have the track, isn't it? You must have the track. Track provides what? Track provides the normal force. Track provides the normal force. Yeah, track provides the normal force in order. You see, this roller coaster is on the track, isn't it? It's on the track. So the track must provide normal force, like a supporting force for the roller coaster. So this track provides a normal force for the roller coaster. So without the track, without this track, how is it possible for the roller coaster to move in a loop by itself? Not possible, isn't it? You must have a track, a roller coaster track, to provide this, what we call the normal force, because this normal force is very necessary for the centripetal force. Yeah, this track provides the normal force, and this normal force becomes the centripetal force for the roller coaster car to move in a circle. Without the track, without the normal force from the track, this car not possible to move a loop, to move in a circular motion, because it is this normal force that becomes the centripetal force to change the direction of this velocity into a circular motion. Okay, similarly, like this road must provide the enough friction. This road must provide enough friction for the car to move in a circle. Like this gravitational force, that means the earth provides the gravitational force. The earth provides the gravitational force for the satellite to move in a circle. Like this one, the rope. Okay, the rope provides the tension force. The rope provides the tension force for to become the centripetal force for the stone to move in a circle. So what I can say is, centripetal force, they are the existing force like friction, like gravitational force, like normal force, like tension. They are all these existing force. That becomes the centripetal force. This centripetal force, they are the existing force like friction, gravitational force, normal force, tension. Yeah, this existing force become this centripetal force for the circular motion to happen. Yeah, for it to be a U-turn, for the satellite revolve around the earth, for the stone move in a circle when revolving around the hand, the grip, for the roller coaster to move in the loop. All the responsible force are the existing force like friction, gravitational force, tension, and normal force. Okay, these are the types of centripetal force we have in our universe. All right, so that's all for our video. Thank you.